I'd like to take a moment right now to look at limits and what they look like on a graph. So if we have a picture of a graph, look at what happens with the limits and what a function does as it approaches values, different values, and the different types of limits we could get. And then we'll spend a little bit of time talking about how we would do those limits algebraically, and then I'll give you some time to work on those. So limits, we talked about this yesterday, but they're a way of looking at how a function behaves around a value. So we're not looking at what happens at a value, but what's happening around it. So I'm going to use this picture for quite a few examples here, but if we just look at this point right here, at the point where x equals 4, y is going to equal -1, the function around the value doesn't have anything to do with its value up here. All right, so this is a function that's defined for every value between 0 and 10. Okay, it has a value for every point between 0 and 10. However, it's not a continuous function. We have a discontinuity here. What kind of discontinuity is this? Removable. What kind of discontinuity is this one? Well, it's actually kind of two. It's an infinite discontinuity because the value goes up to infinity here. This vertical line is an asymptote. It kind of looks like a jump discontinuity in a way because it jumps down to the value of 7 then here. And this is a removable discontinuity. All right, so the discontinuous points are the ones that are really interesting with limits. If it's a continuous point, the limit of the function is just the value of the function. So like here, the function's continuous, so the limit is just going to be whatever the value of the function is, which is, in this case, 3. So the limit of f of x here would be 3. What's interesting is where the function is discontinuous. Like here we have a removable discontinuity. So when we're dealing with a limit, we're looking at what this function is doing around 4, but not at 4. So what is the value of this function around 4? 1. Okay, now, is the value of the function actually ever equal to 1? It's kind of hard to tell to the right here, but it's actually a little bit below 1 here and a little bit above 1 here. So it's never actually equal to 1. But you can see that as we come from the left, it's getting closer and closer and closer. So the closer the x value gets to 4, the closer the y value gets to 1. And from the right, the same thing. It gets closer and closer here. It never actually gets to 1. It stays just a little bit below it, but it can get as close as we want to it. Okay, so the formal idea of a limit really sets threshold values, meaning we could say any arbitrary number, say 0.01, and we can make the value of this function get within 0.01 or 1/100th of our limit value, which in this case would be 1. So we could say if I want the value to be within 1/100th of 1, I have to get this close to it. And you would have to do a little bit of math maybe to figure it out. But it involves very small changes. And we could say instead of 1/100th, we want to get within 1/1,000,000th. And we could do that as long as we get close enough to 4. Or we could get in, within any value that we want. All right, so that's kind of the idea of the limit here. So I'd like to look at a few examples. Okay, we're going to use this graph for all the examples. And we're going to talk about how we would evaluate this limit looking at the graph, but it's also going to apply and help us with how we would evaluate the limit if we had a function. So if we were going to do it algebraically. So this first one I think is pretty straightforward. The limit as x approaches 5 of f of x. Remember this function right here in the graph is f of x. What's happening to this function as we approach 5? It's going to be 1, right? Now, this one's really straightforward because it's continuous at 5, meaning that to the left of 5 and to the right of 5 and at 5, all of those points are in the same neighborhood. They're all strung together. So we can just use the value of the function at 5 as the limit. Now, even if it wasn't defined at 5, let's say I took this point and moved it up here and just had a hole there, the limit would still be 5, right? Because of what's happening around it. Okay? What about when x approaches 4? We just talked about this one. It's going to be 1 still. So even though the value of the function itself is 5 when x equals 4, the limit, meaning what's happening around it, is still going to be 1. All right, because we can see that it's approaching 1 from the left here, and it's approaching 1 from the right here. All right, and this idea of approaching from both sides is really important. This is what's called a two-sided limit. If we have this notation, the limit as x approaches some constant, it has to approach the same value from both sides. All right, so how about the limit as x approaches 2? Right now it's pretty easy because we understand limits. I will tell you that later on in the year, a lot of you are going to want to say it's undefined. Because the derivative is actually undefined at 2, and a lot of people start getting those mixed up. But the value from the left is approaching 3. The value from the right is approaching 3. So the limit of the function approaches 3 as x approaches 2 from both sides. All right. How about 7? It does not exist, and that's exactly the terminology we're going to use. So the limit here does not exist. And here's why. Remember, we said if the notation looks like this, where we have x approaching some constant, then it has to approach it from both sides. And from the right side, the value of the function approaches 0. In fact, the value of the function at 7 is 0. Okay, so from the right side, the limit is 0. But from the left side, we have this asymptote here. So as we get closer and closer to 7, the value of the function increases without bound. All right, so it can be infinitely big. So we have an infinite limit on one side, we have a finite limit on the other side. The limits do not match up, so the limit does not exist. The limit only exists if it's the same on both sides. All right? So what we can do here is talk about one-sided limits. So rather than just saying the limit as x approaches 7, we can look at what's the limit as x approaches 7 from the right. So this right here, this notation means from the right. And so we're approaching 7. We're looking at values just a little bit bigger than 7. And what is the function approaching here? 0. Yes. So this limit right here is defined. It does exist on the one side. So that is 0. Okay, does that make sense? So we're going to run into this a lot where we want to know what the limit is just on one side of a value. So this is called a one-sided limit. We can do the same thing from the left. So the limit as x approaches 7 from the left of f of x is looking at what happens to the function with values just a little bit less than 7. What do you think this is going to be? Infinity. In this case, this is one of the times where we can use infinity as kind of a number. Remember, I've said before, infinity is not a number. Infinity is an idea or a concept. It means without bound. So what this means is as we get closer and closer to 7, the values of the function increase. And we can pick any maximum value we want. We could say I want that function to be more than 1 Google. And then we could figure out some value close to 7 that if we pick that, it'll be bigger than a Google. Not the company, but the number. Okay. How about 9? What is the limit as x approaches 9 from the left of f of x? It is 1. Okay, so we can see here as we're approaching from the left, this function is approaching the value of 1. Never does get to 1, does it? Okay, but it approaches 1, and we can see it's going to get, if it continued the way it is, it would get to 1 when we get to 9. How about from the right? Also 1. So as we approach with values slightly bigger than 1, never does get to 1, but it gets close to it, and we can see if it continues as it's going, it would be 1. So the limit as x approaches 9 from the left is 1. The limit as x approaches 9 from the right is 1. So what is the limit as x approaches 9? 1. So if the two one-sided limits match up, then the two-sided limit exists and it has the same value, would be 1. We just looked at how we would do all this on a graph, but you guys have enough understanding of what the basic graphs look like lines, parabolas, trig curves, exponential curves, rational functions. You guys have a good enough idea of what those look like. You know when the asymptotes are going to happen, where they're going to happen. You know when the holes are going to happen. to know what the picture is going to look like. So if I gave you a function written algebraically and not as a graph, you should still be able to answer these questions because you know what the graphs look like. Do you agree with that? Okay.